To study optimization tools, we really do need some kind of motivating example. We're going to start with a problem with a known formula. And so this is already fairly simple for optimization tasks. In fact, this is simple enough that we can use the analytic methods from APSC first year courses, taking the derivatives and setting them equal to 0 to find the critical points. And then you do additional work afterwards to classify the critical points as local maxes and mins, all that good fun stuff from first year. We're going to save you that grief and just recognize that we have 4 local minima. And through this process, we know their x and y locations, and we can see their function values. This means that the points here are locally below any points nearby, but we can see that one of the values, 77.2, is smaller than all these other values. And so that lets us know that this value here, out of the 4 local minima, there's one which is a global minima overall. So that's the context. We have a function that we can evaluate. We can use analytic solutions to find local minima and global minima. And what we'd like to do is see how we can identify these same points without calculus using the numerical methods tools built into MATLAB. To give us some context, here's a picture of the surface. It's a little easier to see the layout of the surface here, and we'll just add the axes for reference. Going back a page, we can see that the x-coordinates around -2.9 and 2.7 were involved. And if we scan over to 2.7, 2.9, we see, right, we're looking at these points here. We can see the heights, about 77 here, a little lower than 120, a little lower than 150, a little lower than 110, it looks like in here. In other words, matching the values that we had listed in the table. Here we just see them graphically. Remembering what the numerical algorithms are going to have to contend with, though, they're not going to know about the surface. At best, we'll be able to pick one x vector, which is really our vector of x and y values, and recognize what the height is there, and then try to take a step maybe towards a local minimum nearby and try to improve the function. Here, minimizing means improving in some way by jumping around on this function until we get down to a basin, the bottom of a basin. On the side here, we can see that would be like walking down the hillside until we find ourselves at the bottom of a valley. So what kind of strategies might help us actually navigate from some random point that we pick to start down towards the valley? Well, what we can do is take advantage of some of the insights from calculus and use the gradient, or the vector of partial derivatives, as a guide. The reason is, if we want to go downhill, we remember that the gradient, which is defined as the vector of all partial derivatives together, always points in the direction of maximum increase. In other words, going back to our chart here, if we'd pick this location here and we could find derivatives, at least estimate them, we could find that the gradient is going to point uphill in the steepest direction. Well, if we want to go downhill, we just go the other way. So, if we have a gradient-based search, that's one where we either can compute, or if we don't have a formula, we can estimate the partial derivatives, and we just follow that gradient backwards until we reach a local minimum. It's not going to be instantaneous, because if we follow this vector back, we're going to be able to find at best a local minimum along that line. Then we might turn and say, well, what about this direction? Now we're getting down towards the valley. Again, we'll need some iteration to happen, but as a strategy for telling which direction out of all the directions we could go in, back down, following the gradient backwards, is at least a reasonable starting strategy for an optimizer. In MATLAB, there's a function that's going to do this for us, and it's composed of 3 different ingredients here. It's fminunc is how I pronounce this. Notice it's saying explicitly that it looks for minima of functions. F is the starting thing, like F0. So take a function and minimize it, and the UNC represents the unconstrained aspect of the search. And unconstrained simply means any x vector in principle is okay or allowed. With that function, all you need to do is provide the formula. So in our case, the f of xy equals. And what this MATLAB fminunc will do, it'll estimate the derivatives as needed. It's also possible if you actually have a formula like we do and want to compute the gradient and produce that as part of the input, you can certainly do that. That's more advanced than we need for this class. If that ever becomes a context that is helpful for you, take a look at the help menu. It walks through all these kinds of scenarios and provides example code as well. We're now going to explore using that fminunc function, or fminunc, by looking at the file w10.1 MATLAB code. And it's going to produce a search for a local minimum, and it's also going to display the function as a contour diagram as we get started. What we're going to do is add the showing of the starting point and the ending point as part of our code. So let's take a look at the code next. We see right off the bat, we have a function of x and y with the formula that we just talked about, or that's in the notes. We then see an interesting addition that's not necessarily obvious that we need it, but this captures the x vector idea. We don't call it x because x has already been used in our problem, so we'll call it v for a generic vector. But we need to have a function that only has one single input. Now, how does that work? Well, if someone hands us a v, let's do it here. If we said we want to start at the point 3, 2, that would be x equals 3 and y equals 2. That's our conceptual idea, and we implement that or use that in MATLAB to work with our function, which does expect x as one input scalar, y as another input scalar, by using this calculation. Someone hands us a v vector, say 3, 2. We will take the first element, the 3, and put it in as the first argument. That'll be what we consider x for all our calculation purposes. And then the second element, v2, is our y value, and it'll end up being the y in this calculation here as well. So we have a function that takes two scalars, but our optimization tool only handles a single input, but that single input can be a vector of multiple values. This is how we achieve the conversion. You give me a vector, I'll break it into two pieces for my function that expects two inputs. Next up, we do our plotting. So this is a standard contour diagram setup where we do a mesh grid over a range and we plot, and then we give it a starting value. We give our optimization search a starting value, and then literally we say, I would like to search for the minimum of a function f in an unconstrained way. What's the function? Notice it's the fv version. And what's the initial starting point? v0. So we're going to run this. And when it runs, it's going to tell us some stuff. It's going to plot the contour diagram. And what we'd like to do is actually display our starting point, which was 3, 3 over here. Notice our inputs are here, 3, 3. And we'd then like to display where we ended up as well. We can see where we ended up through the vopt and fopt outputs. Let's take a quick look at those as well. vopt is a vector. That's the name v. And it has two values. Not a huge shock. Those are going to be our x and y values. And the fopt is the value of the function. We can go back here and quickly compare those values to what we found in our table. So the exact values. We're at 2.7 and 3.8. If we scroll back up to our function and its properties, 2.7, 3.8, here we go. We should find a minimum there, a local minimum of around 144. And sure enough, there we are at 144 for the height. So this numerical optimizer search worked, and we'd simply like to enrich that a little bit by plotting some values, like plotting the starting point. And we'll plot that based on our v0. So we started at 3, 3, looking at these values here, and then we're going to plot v0, the x coordinate, so the first coordinate, v0, the second coordinate, that's the y coordinate, as say a blue dot, and a little bit bigger than default, just so we can see it. And we're also going to need a quick hold on up here so that any later plots actually show up. Let's try that first. We'll run with a quick typo. There's a negative sign missing. Run that again. And we see, there's our starting location. We'll make the dot a little bit bigger next time. Make it 16. And then we'd also like to plot the output value. And that is, looking at our lines, we calculated the minimum search results based on our function starting at v0. We ended up at vopt. So vopt1 is the x-coordinate of our optimal answer. vopt2 is our y-coordinate. Let's do a red dot for the output. And again, a little bit bigger than default so we can see things. Save and run. And we see perfect. We start at this location here. We end up down at this local minimum in the contour diagram. It's lower than any of the points nearby. Going back to our notes for a moment, our function x and y, what we created was a function of v, which we called fv, which was a vector, and the translation just, or at least very similar to what we did with differential equations, is we built a new vector or a new variable that contained the other values in it. So every time we see v1, that's the same thing as saying x. Every time we say v2, that's the same thing as saying a y-coordinate. So as long as we have that translation in mind, that's how we can get our function to only have a single input. The other interesting ingredient is there's a lot of text actually that comes out at the bottom of our calculations. We run our script and it says local minimum found. That seems promising, and in fact is validated by what we saw in the contour diagram. That appears to be a local minimum on the contours. But it also tells us the optimization completed because the size of the gradient is less than the default value for some tolerance, and so there's some stopping criteria. Well, you can imagine as we walk around on this surface and are jumping down towards this minimum, there's no magic rule that says we are at the bottom if all we can do is test single points. Maybe there's some little path out that we can't see where things go down even further. So the best that MATLAB can do, or any numerical solver or optimizer, is try a bunch of points, try to estimate the gradient, and if the gradient seems like it's pretty close to all zeros, all the derivatives are close to zero, then it says, well, maybe there's more work to be done. If so, you'll have to tell me, but I think we're at a local minimum. And that's all this text here is capturing, so you know how reliable the output is right now. Best or default interpretation is that we are at a local minimum. It's that the point found is a local min. We didn't stop for any other reason. We stopped because we think we're done, but you should check your work afterwards. And there's no reason for concern with that at all. Sometimes people do take a look at that output and think MATLAB's telling them that things are broken. Absolutely not. Local minimum found. Good. I'm looking for a local minimum. This is just a few more details about why it thinks that's actually the case. Now, one important note, of course, is that with calculus, we found all 4 local minima. With this approach, we only found 1 because each starting value, we pick starting value, there's going to be some kind of downhillish search, and we're only going to find 1 local minimum as a result. How would we find these other 3 local minimums? Well, what we have to do is choose new starting points. Choose or try new starting values. Let's do that quickly. Looking at our contour diagram again, if we started, say, around here, let's say -2, -2, we change our initial values in the formula here in our function to -2, -2, and we run that search. Then we are now starting at this location on the contour diagram. The search is going to be downhill, and it ends up, as we expect, in the basin that is closest to, or that this would flow into if we were going downhill the whole way. If we wanted to search, say, up at -1,6, actually off the contour diagram here, -1,6, we could find another local minimum that way. Here's our point. If we went downhill, we would roll into this basin and find this local minimum. And notice that they're at different heights. This one was around 144. This is close to 115. This one was down at 77. This is actually the global minimum. And that begs the question of how do we look for a single global minimum? There's no easy way. One answer is to do lots of optimization runs with different starting points. And the other answer is to know our domain or our application area. In some contexts, you have a good idea as to what a very good design is, and then the optimization can help you refine that even further. But you do need to start with something reasonable. The closer we start here to the global minimum, the more likely we are to end up at that global minimum. If we start far away, we do find a local minimum, and that's fine, but it's not the one we might consider the absolute best solution to this problem. What's the absolute lowest I can get on this graph? And that's because we didn't start close enough to the point that we were looking for. If you know your application area, then you're much more likely to be able to hone in on the optimal answer, overall optimal answer.